Okay, so we're going to start now on page 83, part 5. That's multiple regression with two quantifier predictor variables. So far what we've been doing is multiple regression, multiple meaning that you have more than one x variable, more than one predictor variable. But we started off in the simplest case where one of those predictor variables is binary. So it's just, for example, the one we used was just male or female. And it was the simplest case, and we could stratify into just explaining it by just splitting the gender, the binary variable, into two groups. And we saw how multiple regression captures the same thing as that stratification. But some of you wondered, well, why are we even doing this? Why don't we just look at the two separate scatter plots? It's so much simpler, especially when you were doing the homework last night and you were saying, why are we even doing this? Why don't we just look at those two simple regression equations? What do we gain by combining them? So in the simplest case like that, you really don't gain much. I just wanted to show you how multiple regression works. But now we're going to move on to, we're still just going to have two x's. An x, in this case, it's going to be homework and exam scores predicting one y final. But both of those are quantitative variables. So if we try, this is an extension of what we did back on page 31, where we just looked at a simple scatter plot where we were predicting final exam scores for 107 students, former Stat 100 students, from their exam averages. And we had a scatter plot. Well, now we say, well, we can do a better prediction if we combine homework scores. But with homework and exams predicting final, we can't, you can't just say, oh, well, it captures the same thing if we just stratified along the homework. We had exams predicting final before, and if we had added gender, sure, then we could have had two. We could have split the data into males and females and see the differences. But with homework scores, we'd have a lot of splits. We'd have to stratify. It's a quantitative variable, homework, so we'd have to stratify to many, many groups. We'd have to separate it into everyone who had a homework score of 50, 51, 52, 53, however many groups you wanted. And we'd have lots and lots of different scatter plots to look at. So you can see why it makes sense now to combine into a multiple regression equation. So that's what we're going to be looking at today. And then we're going to take it even further, and we're going to have more than two predictors. Some of them quantitative, some of them binary, some of them with more than two categories, and combine them all into a model to make a prediction for a single y variable. Right now, the y is quantitative. All right, so that's what we're doing. So let's look at this. So it says here in simple regression, we drew a scatter plot to show the relationship between two variables like that. Now suppose we want to use, that's simple, just one x. Now let's say we want to use two x predictor variables, all right? And now they're both quantitative. And we saw before that these slopes, for how much of an effect each of these x's have, are not, these like b1 and b2 are not the same as they are in the simple regressions. That's true even when one of them is binary. So here's an example. We're going to expand on the simple. So we should say that we can't just combine, homework predicting finals and exams predicting finals and keep those same slopes. So they change. So let's expand on that simple regression that we did before. I think it was on page 31. I can just check. Go back to page 31 here. It was a while ago. Yeah, we started with this. we said we have 100, and here we only had 100 students. I sort of rounded everything here, but it's basically the same example. There were actually 107 students. And here we're predicting final exams from their midterm averages. All right, so now it's the same thing. It's actually a group of 107 students. So now we have two variables. We have an x. I just got to get a better, that pen doesn't have ink. Okay, so now we have an x1 and an, oops, x1's here. Let's call homework x1. Let's call exams, that says x sub 2. And here's our y variable, which is the final. And here's this correlation coefficient right here. Now, what is this correlation coefficient? For simple regression, remember what the correlation coefficient is? It's the product. You change the x's and the y's to z-scores to get a common measuring stick. They might not even be in the same units. For example, if you're predicting height from weight, you have to change them both to these z-scores, standard measuring stick, and then you you multiply the z-scores for each. If you have 107 people and you took height and weight measurements, you'd multiply the z-scores for each of the 107 people, and then you would get, you take the sum of those 107 products and their average, and that's what a correlation coefficient is. But now, what if you don't have, what if you have 3 variables? Like here we have 2 x's and a y. So how would we do this? Because the correlation coefficient's only defined with 2 variables. So, and it's between -1 and 1. It can be either positive or negative. But for multiple regression, I'll call it capital R, it's the correlation between 2 sets of variables, and what the 2 variables are for multiple regression are your actual y's, your actual, in this case, your actual final exam scores for the 107 people, and y hat, which is the predicted final exam scores for the 107 people based on our model. Okay? So this is the only type of correlation that makes sense when we have more than one x variable. So for simple regression, how do those two relate? How does this capital R relate to the simple regression we figured out before? For example, we know how to, if we computed it this way for just exams predicting final, how would it change if we used capital R and looked at the correlation between the predicted finals based on exams and the actual? Well, it would be the same thing, except it would be the absolute value, just the positive. And that makes sense, because it's a correlation between how closely your predictions match your actual, right? And we're going to be trying to match them as closely as possible. So even if it was a negative correlation to begin with, when you make a predict, it's going to be the same, it'll have the same value, it'll just have a different sign. For example, like let's say I wanted to predict, I don't know. So if I could make a perfect prediction for how many questions you answered right, how many points you got based on how many you got wrong. In fact, when I give you back your exams, I always say we tally up how much you got wrong. And if you got 5 wrong, that means you got 95 right, 95 points correct. If you got 6 wrong, you got 94 correct, et cetera. So it's a perfect -1 correlation. And if we computed it, that's our usual way. It's perfect. It's -1. We would just get, if we computed it by looking at the correlation between the predictions, if we computed it using capital R, we just always get +1. We just get the same thing, just the positive direction. Okay? So they're the same. Little r and capital R are the same. And we've been using this capital R in our, when we do those chi-square and F tests. All right. So now they're the same for simple regression, and for multiple regression, though, they have to be calculated a different way. So suppose we want to predict final scores from exam and homework, and we use this multiple regression right here. Okay? So now R is the correlation between these finals and your actual finals, right? But there's also 3 little simple correlation coefficients that are not the same as R, and that's the correlation between each of the 3 variables, between the the correlation between your y variable and one of your one of the x's, the correlation between your y variable and the other x, and then there's this, the correlation between your 2 x variables. So this is what R is. Capital R. It's the multiple correlation coefficient. That's what it's called, multiple correlation coefficient. And it's that, and squaring it is what we've, it tells them strength of your model, right? And 1 minus R squared is the strength of the errors. It's that same capital R we've been using all along when we talk about analysis of variance. All right. So now what we're going to do is just take a quick look at the 2 predictor variables separately. Okay. And so what do we have here? We have our final exam being predicted by the homework predicting the y, and the exams predicting the y. And we have 2 equations here and 2 graphs. And they both show a positive trend. All right, so what do we gain by combining them? Well, we can make a better prediction, of course, when we combine information. We did that before. But we also can look at the effect of each predictor variable, and this is really important, while controlling for the other variable, keeping the other variable constant. Okay? So we can, and what we did previously was we showed how that worked by stratification. We said, okay, what happens when they're all males? What happens to, does a bigger foot mean that the male's going to buy more shoes? What happens when they're all females? Does a bigger foot mean that the female's going to buy more shoes? In general, we saw it didn't really have any effect. The effect was just due to being male or female. That was the example we used. But now, so now what are we going to do? We're going to say we get a different coefficient when we control for the other predictor. And we certainly do. Once we put gender into that equation, that huge negative slope that said the bigger your foot, the fewer shoes you had, just completely disappeared. We got something different. Okay. So here's a multiple regression equation. Let's look at this. For predicting right here, this one, let's look at this. This is the multiple regression equation. And how are these slopes calculated? Well, they're pretty hard to do. We're going to explore them a little bit, but we'd have to adjust for all the r's and the standard deviation. Like before, we could just say r over the standard deviation of, remember, to get a slope in a single regression equation, if you recall, we just look at the correlation between these 2 r and then multiply by standard deviation of the final divided by standard deviation of the homework. But now it's going to get very complicated. If we do, we'd have to adjust for all the r's and the standard deviations we used before to account for the additional variable. And the calculations are very tedious. I can show you a little bit of how it works just so you can get a feel for it. Okay? So, let's see. First, let's look at this. And do we have the same slopes as we did for this simple equations? Let me zoom out a little bit so you can put this all on one page here more easily. All right, so here's our 2 simple regressions, right? And the question is, are these two slopes the same? Like we're comparing the slope for homework right here to the slope for homework right here. Is it the same? No, what happened to it? That one's different. It went down. It went down from 0.3436 down to 0.1641. How about here? Let's look at what happened to the exam. It went from 0.6647. That went down too. No, they both went down. Okay? Both went decreased. That's not always true. They're not always going to both decrease, but why did it happen here? Why do these slopes change? That's what we're going to look at right now. Why did they change? And the idea is they change because they take into account how the two x's are correlated. That's why they changed right here. They take into account how they are correlated. So first of all, let's look at something called a correlation matrix and see how they're correlated. See how everything's correlated, all right? So this is what's called a correlation matrix right here. And here's x1, x2, and y. And this is x1, x2, and y. And you can see it shows how each of these three is correlated with each of these three. In a correlation matrix, down the diagonal is always going to be 1. Do you understand why? Because if you read this down the diagonal, it tells you what? Yeah. You read it like homework is correlated with homework. If you know somebody's, that's perfectly correlated. And this one is exams are correlated with exams. And perfect correlation, 1, and final with final. So you'll always see that down the diagonal. The other thing you'll probably notice, is what? Look at the off diagonals. What do you notice? That like these two. Do you see? And these, the two, and those two. See how they're exactly the same? Why do you think that is? Why do you think they're exactly the same? Because, well, let's look at this one right here. Why is this one the same right here? We'll look right here. Well, that says the correlation between homework and exams. And what do you think this one says? The correlation between exams and homework. It's the same thing, isn't it? Aren't those two the same things? Does everybody understand that? And like this one, if you wanted to read that, this would be the correlation between homework and final. And here you could say between final and homework. So they'll be the same. Okay? Do you understand the correlation matrix? How to read it? All right. Now, what I'm talking about here is why do the slopes change? They change because they take into account how how x1 and x2, they're taking into account this one right here, x1 and x2. That's how that they have a non-zero correlation. That's what's going on here. That if they had a zero correlation, if they were completely uncorrelated, if homework in other words, if people had high, you couldn't predict from somebody's exam score what their homework was, if they were really uncorrelated, completely uncorrelated, well then these would be the same. Because but what this does, and I'll explain more in a little bit, the simple one doesn't, like if you just look at this effect, what is the slope saying? For each additional homework point that somebody has, like as you go from a 66 to a 67 homework average, okay, this 0. You'd expect 0.3436 additional points on their final, on the average. And this says, just looking at this slope, it says as you increase exams, somebody's exams increase by 1 point, their final, on the average, their best prediction for the final increases by 0.6647. So that's a stronger effect. They're both basically in the same unit, so exams have a stronger effect, and that makes sense. Now, why do they both go down when we do this? Is because each of these are not controlling for the other. So since there's a positive correlation between these two, part of the effect of this, is due to the homework, and that's this part called the partial slope. But part of it's due to the fact that these two things are correlated. The people with higher homework scores also have higher exam scores. So these are like the partial effects. When we say this is very important. When we say we look at the effects of each predictor while controlling for the other predictor, we mean that once we, let's say, for example, once we make our prediction using this, what's called a partial slope. This is just looking at exams alone. It's subtracted out the effect, the correlation between homework and exams. Then we say, well, how much does homework help us make the prediction? So for example, if we look here, part of this, this is mixed together. This is not controlling for homework. So this is a very nice way that a multiple regression equation separates out the two factors so you can see what's due to what. Whereas here, they're mixed together. We saw that in a dramatic effect of confounding when we saw back in the shoe example that when we split it into a multiple regression equation, or that, I guess, did we do it for that one? Well, we can do it for this one. When we saw that when we split it into the multiple regression equation, the slope really, really changed. It disappeared for shoe size. Okay, so that's the idea. And I think maybe if we just do a little bit of, explore it a little bit more, maybe you'll understand what I mean by these partial slopes separating out the effect. So we're going to just try to look at that a little bit today with the same example. So first of all, here's another scatter plot. Here's our third scatter plot, and this one is doing what? This is looking at x1 and x2. And we said they're correlated, and for sure they are. And there's that correlation coefficient. Okay? And so we have that too. Now, so focusing on, so here's our multiple regression, right? And we can see, it might be, I could show you if you'd like, how here you get the two partial slopes, the part that's just due to homework alone and exams alone, whereas here, for example, in this one, this slope is bigger because it's combining not only this piece that's just due to homework, but also the correlated part of that one. The correlated part of that one. I can show you how we can go from one to the other on the next page. So let's do that. So now we're on page 86. And this is just to help you understand it. As I told you before, these slopes are going to be given to you. And I'm actually not, it's easier just for me to show you how to get from this multiple to the simple. So I'm this is just an explanation. The slopes are always going to be given to you. Yes?
So if having more variables in your multiple regression equation increases your ability to predict, why would you even bother blocking? Why wouldn't you just always do multiple regression?
Very good question. He says if multiple regression helps you predict better, why would you ever do blocking or stratification too, right? Do you mean that too? Why do you even bother with that? I think if, as I said before, if you have a very simple case of an observational data, right? Let's say it's like this, not a randomized experiment. We would stratify. We stratify. Why don't we just do this multiple regression to get at what's going on? They'll give you exactly the same thing. The problem is that when you stratify, each time you break it down into smaller and smaller groups, and like, if we wanted to stratify here, so we wanted to look at the effects of exams, controlling for homework, we'd have to stratify into how many different plots. See how many it would be? So it would be so it just depends on, so why don't we always do this, is what you're saying. Well, sometimes, why would we do stratification? We usually do stratification just to give us when we don't have these quantitative variables, but we just have the binary or a few groups and we just want to see what's going on. It gives you a very clear picture of what's going on. Does that help?
So it's for binary variables.
Yeah.
If you have quantitative, it's better to add more variables.
If you have quantitative, you could stratify, and people do this all the time just to get a feel for what's going on. You could stratify into those who have high homework, middle homework, low homework. It's nice to get a simple visual. And sometimes, as you see, when you do these models, it's very hard to tell what's going on, especially when you start adding more variables and they're correlated with each other. So you can make these models that are very hard to interpret. And sometimes when you just do this stratification, you'll say, oh, I can get a better feel for what's going on. Does that make sense? Okay, any other questions? They're not either or. People do both. They particularly often make models, and they, like in randomized experiments, they block. They use all the tools they can to figure out what's going on, all right? All right. So now we're just going to see, look at this. And what I was just going to show you here was how we get from this right here to this. Like we're taking what we're going to be doing here. How do we get? We have this piece. We're going to add to it. To get to this, we're going to add to it the part of the exams that's correlated with the homework. So we're going to look, so here we start with this model right here. And then we say to get to this simple model, we want to eliminate this exams. We want to just, okay, and we want to express that in terms of homework. So we have this equation. How can we get this equation? Well, on the previous, it says see previous page. What did we do on the previous page? Let's look at the previous page. What we have to do to get this is we have to, this is the slope, it's R, and it's R between what? Homework and exams, right? That's R between homework and exams. I'll say between x1 and x2. And it's going to be times the standard deviation of the exams. We're calling those, I guess this is, we're thinking of this as x2 and this is x1. Okay, so now it's going to be a standard deviation of x2, or exams, over the standard deviation of x1. Homework over, I'm sorry, this is making it, it's probably easier to just say exams and homework. We're predicting that. So what is that? That's how we're going to get this slope. Well, we can look back at our correlation matrix here, and we can see that the correlation right here between the homework and exams was 0.3933, so let's use that. And then we're going to look at the standard deviations, which we were given on the first page, and we want the standard deviation. Here are our two standard deviations. So it's going to be 9.197 over 11.73. Because, okay, so let's remember all that. And that's how, I just want to show you where that came from. So that's going to be 0.3933 times the standard deviation for the exams was 9.197. Over the standard deviation for the homework was 11.73. Any questions on that? And when we do that, if you do that out, that equals this. That's how we get that equation comes from. And then there's an intercept. An intercept. So when I say see previous page, I meant do this. The intercept is we're not worried about too much. It's going to change, but we don't really care about that. We're looking at how the slopes change. All right, so now we've got that. And so what we're going to do is just substitute it in for exams right here. So see this exams right here? We're going to just substitute this in for it. And then won't we have something that's completely in homework? See, we did it right here. So we took this right here. This right here is that right there. So when we multiply those two together, we get that. And add them, and there's where we get a bigger slope in the simple one. You can think this is the effect due to homework alone, right? Right here is the effect on finals due to homework alone. And this piece right here, what is that? That's the effect of the homework that's really, it's passing through the exams to affect. It's really, this is because they're correlated. So this is the effect due to the fact that people with, every time that when you add people with higher homework scores also have higher exam scores. So this is the effect really due to the exams, not really the homework. And it looks like it's due to the homework. All right, and this is when they're all mushed together here. So before you control for it, this is a very nice part of multiple regression. When you just look at the simple, you can't separate these out. But in the multiple regression, it does separate them out. All right, so that's what I say here. I explain it probably a little more detail here. I say, let's say we compare students with a 70 on the homework with some that have a 71. So they go up 1 point in the homework. Just from the homework prediction alone, they'd go up that amount on the final. But remember, homework and exams are positively correlated. So that same batch of students we're looking at who go up 1 point in their homework not only have higher homework scores, but they also tend to have higher exam scores. How much higher? Well, that is the this right there. So that effect also raises it by that much. That's what I meant when I said effect due to the exams. That's what I meant. You should probably just, that's what it's. So when you add the two effects together, this is the one completely due to homework alone, and this is the effect through the correlation. That's what we get, and that's exactly the slope we get in the simple regression. If you just look at how much these people's finals went up per homework point, without controlling for exams, if you don't think about exams, that's what it looks like. It's a bigger effect. Then here you see what's due to each one. All right. Because, okay, we can do the same thing here. Do you want to go through it here, or do you want to just do it on your own? Do you want to go through it? Raise your hand if you want to go through this now. Do you want to do it again? Okay, I think there is a problem. I'm sorry, I haven't released your homework yet, but I will. And there is a problem like this, so it would probably be a good idea to go through it again. All right, so let's start okay, so the first one is start with the full model. Let's go to step 2. Step 2 is to get to the simple model. We want to eliminate homework now, right? We want to eliminate homework. So we have to get an equation that's relating homework. I want to put that in terms of exams. So I want to get some slope times the exams plus some intercept. And then I can substitute that in, and I'll get something all in terms of exams. All right, so what's that slope going to be that I put in there? Well, that slope is going to be that same R, isn't it? Just homework and exams R, so that's 0.3933. But now I'm predicting, now homework is Y. So instead of having, this is the standard deviation of exams over the standard deviation of homework, so I can just flip those two. Does everybody understand? So it would just be, the slope would be 11.73 over 9.197. I should probably put in the units. That would be homework per exam scores, and then the exams cross out, whereas here it's the opposite. All right, so when I did that, multiply that out, I got 0.5016. So, questions so far? And that's homework points per exam. We're trying to get homework. All right, so that now, what am I going to do with that? Well, now I'm going to substitute that in for exams, homework here, and then I'll get something that's just in terms of exams. So that's step 3. If I follow the steps here, I'm substituting in the full model. So I have final is equal to, and the full model says 0.1641 times the homework, but I'm going to substitute this in for homework right here. So it will be 0.5016 times exams. I just want to get everything in terms of exams. Right? I just substituted for that. And this is the same thing as this. That's what I'm doing. I'm substituting. All right. And now, plus I have to add on the rest of the exam. This is the effect that's due strictly to the exams. This is the part of the homework right now. It's really because it's correlated with exams. Now this is the part, add on this part, 0.5824 times exams, and plus some intercept. The intercept, I'm just writing, it's not the same intercept. Well, it's the same intercept there, but it's, I should have added that one too, right? So it's no longer the same intercept. And then I'll just simplify this, and here you get two pieces. So here you get this part, which is very small, when you multiply those two together, this is 0.0823 times exams. And then this is the part that's strict. This was the part of the exams that was really due to the homework. Now this is the part that's due to the exams. The part of the effect on finals that's due to the exams. And then I'll add those two together, and I should get, when you add these two together, I should get that right there. And I do. So that's the idea. Okay, so I think when we see a picture of all this, it will be more helpful. So now we're gonna look in 3D. We're gonna look at how what it means, what it looks like, and what the scatter plot looks like, what it looks like when we control for the other variables. So I want to get to that, but first let's look at the summary here. So so far we have not talked about interactions yet. We're going to bring that in later. We're not talking about interactions. We're just talking about assuming that the effect on, for example, the effect on exams that slope will be the same. You'll have parallel lines that will be the same for every level of the homework. So these are called the main effects. These. If I wanted to add an interaction term, there'd be a multiplicative effect. You'd have to multiply the x variables times each other, like we did before with the binary variables. Now, multiple regression assesses the effect of each predictor variable while controlling. This is very important for the other predictors. That means keeping the predictors constant. All right? Now, if different x's are correlated, like we saw, then the coefficients in the multiple are not the same. If they're uncorrelated, they would be. So these slopes, when you are in the multiple regression, are sometimes called partial slopes. I like that idea. I like that word because I think it helps you understand what's going on. So it's called partial slopes since they quantify the effect of each x variable on the response variable y after the other variables are partialed out or controlled for. So they're separating all the effects, partialing them out. So I like that term because I like terms that help you understand what's going on. So many of the terms are just seem to be don't have that effect. Oh my goodness, I think, is this, oh, it's about to die. This has happened to me a bunch of times. I'm going to change it because then you know what happens? I have to come back and film the rest of it because for all the people, for the whole class, the online class, because they won't hear a word I'm saying. It's so annoying for me. I have to do so much extra work and then I have to find the time this room's free. It's really... So now we've got that down, and now, so what are we going to look? I love this. I'm just going to highlight it because I think it helps you understand it, the language there. Now, so this is what we're going to look at. That we haven't talked about interaction terms yet, and so without an interaction term, as we saw before, it forces all variables in the model to have the same slope for all levels of the other variables. Right? We saw that when we when we stratified into males and females, we saw that if you don't include an interaction term, your equations you have to have the same slope for each. You can't, an interaction term allows for different slopes. Under some circumstances, multiple regression can be used to separate the causal effect of x and y from the confounding due to other x's. And that's something we'll look at. You have to make sure that the x's happen first, for one thing, before the y. And this is really important because beware of multicollinearity, because it relates back to the question that was asked before. Well, why do we even have to worry about stratification or really understanding what's going on? Doesn't this always tell us exactly what we want to know? Well, it can make a prediction, but in the sense of understanding what's going on, it might not do the best job at all. It can be very confusing especially if the x's are highly correlated. So if two predictor variables are highly correlated, the homework and exams aren't that highly correlated, but if they're highly correlated, don't put them both in the same model. And one nice way of, an obvious example would be, for example, your right foot size and your left foot size are both good predictors of height. You'll get a very strong correlation between either one of those and your height if you use them separately. But if you put them both in a multiple regression equation, because they're so highly correlated, they're almost the same thing, either one or both could end up being completely not significant or even have a negative effect, because what it's doing is it's looking for the best. There's so many, it's going to fit some random noise. There's so many, if they're saying almost the same thing, if they're saying exactly, that many different linear combinations of the two are going to make a good predictor. So the linear combination of the two, adding the slopes that they find to make the best prediction for your height, is pretty much dependent on the sort of random noise in your model and not fitting anything that you're interested in. So you'll see this all the time. So you have to be very careful about what happens to these. It's hard to interpret the slopes in a model. Okay. So let's now move on. And now we're going to interpret these slopes when there's no interaction terms here. And we're going to take our same example, and then we're going to we're just going to follow this example through. All right. So first, let's understand these parallel slopes. All right. So the slope for each predictor controls for the other. Think of it this way. So we have observational data here, and the high and low homework groups are not balanced, right? They're not. They don't have the same distribution of exam scores in the two. So those with higher homework also have higher exam scores. And the higher final exam scores are partially predicted by the higher homework and partially predicted by the higher exam scores. So the slopes in the multiple regression, partial slopes, they're called that since they quantify the effect of each variable after the other one is partialed or controlled for. I'm just repeating what we already know. Okay, so the homework slope in the multiple regression, this homework slope right here, where's the homework slope? Down here, this homework slope, like for example right here, the homework slope describes the effect of homework on finals for those with the same exam scores. Oh, here it is, right here, this homework slope right here, for the same exam score. So for example, you have here are these three lines here. This is for people who have exams equal to 90. This is people who have exams equal to 80. And this is people who have exams equal to 70. All right? And now what am I looking at here? What I'm saying is this slope, see this gradual slope of 0.1641 is the same for each one of these. So this is our multiple regression equation here, right? This is the multiple regression equation. And look how it plays out for, if I want to see the effect for 90, for people who have exams, 90, you plug a 90 in there. You plug a 90 in here, and you get the final is equal to 0.1641 homework, plus this 90 is just an intercept, right? 90 times 0.582 plus 11.91. And that would go right in here. Okay? So I'll just do it for this one. So this is, so I'd say 0.5824 times 90 plus 11.91. And I'd do the same for 80, the same for 70. And you could see what's going to happen, that each of these are just going to differ by how much. This is going to be the same thing except times 80 and 70, so it'll differ just by 5.824 points in their finals. So when I did this together, I got an intercept of 64.326, and then I did it here, and it's just going to be plus, it's just going to be 5.824 less than that. I'm just going to write, I got 58.502, and now if you put a 70 in there, I got 52.678. It's about 6 points less each time, because that's, 10 points in your exam is about points, that's about 0.6. So it's about 10 points less, so that's the difference. And the slope is the same, and so this is a multiple regression equation. This is multiple regression, and here's what it looks like. They have parallel slopes for different values of the homework. Okay? Does that make sense? All right. So that's what it says here. The multiple regression equation estimates these final scores from homework scores for each separately, assuming equal slopes. This is not necessarily true, though. We're just assuming this. Well, when wouldn't it be true? It wouldn't be true if, like, people who have higher, maybe doing the homework is going to have more of an effect for people. See, it says the effect is the same, whether they're they're low exam or high exam. It might have more of an effect, I would think, for people with lower exams. It might help them understand it more. They really need to do the homework more. I don't know. So it might have a higher slope. It might be different depending on where the exam scored. Then you would want to include an interaction term. All right? So now if you just look at this simple, here we're looking at this. See how this slope is. Now, what happens, this is simple. This is the one we looked at before. Without taking into effect of the exams, this has a stronger slope. Why? That's because, here's the visual of the mathematical thing we just did. That has a stronger slope because when you look at these equations here, right, these are those multiple regression equations. The people who have the higher exam scores also they're up here. They have a higher homework scores. They're correlated, and so you get this, and they have a higher final. You get this effect. Let's read it. The simple regression equation estimates final scores ignoring exam scores. Ignoring exam scores. It's not paying any attention to exam scores here. So if you just looked without it, without the exam scores, you wouldn't see this. You'd see this. So you can't tell how much of the exam scores account for the increased finals and how much the homeworks do. The multiple regression takes it into account, but this doesn't. And that's why it has a stronger slope. Including exams has the effect of breaking the population into subgroups so we can compare more balanced groups. So that's the idea here. All right? Does that make sense? Okay. So now, let's see. Now we could do the same thing here. Maybe we should do some eye clickers too and look at the visual on the computer. Let's see. How about we finish this page, then we go to the computer. So we're on page 90. We're going to go the whole time because I don't want to lose. This is all connected, and then lots of times it makes sense to break things up pedagogically, but right now I think it will be worse, even though it's really hard to concentrate for this long. So you can stretch or something. I don't know. I mean, I could take a week. I think we need a little break because I can't even concentrate for this long. So we're just going to look at this picture on the computer, okay, what it looks like, and then we'll go back to this. And maybe we can do an eye clicker or two. Okay, so let's look at this. So this is what I did here. I said, okay, let's get this out of here. So what I did was I went to, how are we going to see, here's the data set. And you can look at the statistics. Gender, why does it have gender? I didn't even want gender. Oh, it's just not a question I asked. Okay, so here's this data set. And I moved to 3D plots. And what I did is I picked as my y variable the final. And then I picked homework and exams. And here is the equation that you have in your notebooks. So what are we doing here? Maybe I'm showing too many things here. Let's just get rid of all this. Okay, so here are the data points. So people have, it's in 3D because we have 3 variables. So what are we predicting? We're predicting for somebody who has an exam score is along here and some homework score. The final is the height here, this axis. So when I show you the points, those are the data points. Here's the predictions, those red points. And they form, we have 3 axes, so we're going to have a prediction plane instead of a prediction line. So that is our prediction plane. And this is an equation for a plane, right? 3 points determine a plane. So your homework, exams, and final. That's a prediction for a plane. That's a line equation of a line. Equation of a plane, sorry. Oh, when I get tired, what happens to me is I know what I'm saying, but I know what I'm thinking, but my words don't necessarily correspond. Sorry if I say the wrong thing. But it's a plane. That's our regression plane instead of a regression line. All right? And now, let's see what else we can look at. We can look at these error lines. Like this person right here, they made a pretty good prediction for that person. But he did a little better on his final. Here's somebody who did a lot worse on his final. He's under the prediction plane. It's hard, so that's the idea here. And here's our separate equations with their correlations, the ones we figured out before. And sometimes you can get a better angle, like on this. You can see better. Maybe that's a better angle. See, this right here is the exams, going from 0 on your exam to 100%, has a very steep angle. And here's on your homework, that has that smaller slope, 0.1641. This has the strong slope. And this person felt they made great predictions for, right? But there's a lot of errors. All those lines are errors. So that's what we're doing. And what should I ask you? While we're here, let's just say, what questions can I ask you? Because I don't have any planned. So let's go back to the notebook and I'll ask you some because I want you to see the questions. All right, so let's look here and see what we're doing first. So the exam slope describes, so we're on page 90. The exam slope, this right here, what is that doing? This will be an iClicker question. It describes the effective exams on finals for those with the same what? Same exam scores, same final scores, or same homework scores. So same exams. So our iClicker question is, what should I put in the blank? Should I put exams? Should I put finals? Should I put homework? What fits in that blank? So I'll start the A, B, or C. So I'll start the iClicker. Okay, this is just an easy one for you to, just because I want to have a break for a minute. All right, so it's what everything fits in that blank there. Hey, I wonder if I can, you can't see the question anymore, right? So I'm going to go back to the document camera, and it's A, B, or C. And let's see if you can see it. Maybe here's an iClicker thing on here. Oh, yeah, I can see it up here. So I can see. And now you have to have, do you want to put in A for exams, B for final, or C for homework right there? What's your answer going to be? All right. Did everybody choose? Oh, I can see it right here, what you're choosing. So far, most people have the right answer. All right, do you see what it should be? I'm going to stop this. So I go, for now, let's just, it's too much back and forth. I don't have a plan. Let me just help you here. This is for learning anyway, so you can change your answer if you want. So you just look here, and it's the same homework scores. For those with the same homework, we're controlling for homework, so the answer is C. I just want to stop it, and let's go back to here. And if I stop it, okay. Well, some of you still didn't change your answer. That's okay. Oh, wait a minute, you still, oh, you can't. No, it's too late now. Oh, no, it's not too late. I didn't stop it. Go ahead, go for it. come on, let's get 100%. There's one holdout. Oh, they're switching. Oh, now they're just being silly. Okay. All right, guys. You guys are funny. Why didn't it say? I guess I had to do that. I didn't do that. So this is how we. Nobody chose A. I think these guys are funny. All right, you're making me laugh. Now, let's go back to the document camera. Okay. So. Now, let's look at those. Now, for those with the same homework scores, the predicted final score is what? For those with the same homework scores, the predicted final points higher for each extra point in the exams. Okay, so this is just 0.5824. That's what that slope says. Now, what does the multiple regression above simplify? To those with the, now we're just going to do the, like before we looked at, we did this, we looked at the same equation, but we said for homework scores of 7, 80, 90. Now we're just going to do exactly the same thing here. So what's going to stay the same is the slope's going to be the same for all of them, and just the intercept's going to change. So just put in the same slope, 0.5824 for all of them, 0.5824. And then what's going to happen is when we put in homework of 70, 80, or 90, these will change. So you put a 70 there, and you know how, I don't have to work it out. I'll do the first one and the rest, but you know how to do this, right? So the first one would just be 70 plus 11.91. And then the next one would be 80 and 90. And so when I did that, I got 23.387. And now this is about what? I'm going to get it about, the next one will just be about 1.6 points higher, 25.038, and this is 26.679. All right, here's a good iClicker question. This equation for this simple regression is this. Why is the exam slope smaller in the multiple regression than in the simple? We know that, but which answer would it be? Like this multiple one does what? This is bigger. So why is it smaller there? So do you think it's 1, 2, or 3? This is like A, B, or C. I just want to make sure you're, and now I've got a, how do I start this thing? I have to go back here. Okay. And, here it is. Okay, so I'll start this going. So you want A, B, or C? We'll turn over to the question so you can see it again so you don't get confused. So which one do you want to choose, A, B, or C? Okay, I think you're almost all done. So let's see, I hope you chose B, right there. And because there's a positive correlation between all three of them. Basically, the picture looks like, I should probably stop the iClicker. Let's see if you get 100% this time. I've never gotten 100% because there are perverse people. Just perverse. And even if I stop it now, I'm not going to get 100%. I wouldn't bet on it, but let's see. I know there's always perversity. You can count on that. Okay, so now we're going to go back here to the document camera. And you know, maybe this visual will help. I'm not sure if it will. But, okay, so you have basically homework. Think of homework and exams. Better visual. You see, you have two predictors, but they're correlated. So there's an overlap here. So let's just do homework and exams. And they're both predicting final. And when they're correlated, and they're all positively correlated, everything's positively correlated between them. So basically, when we separate them out, the effects of each of them in the multiple regression are going to get smaller. like alone, if you just look at homework alone, it's going to, or exams alone, it's going to be bigger. But when you separate them into the multiple, you're not double counting that. When you separate it into the separate ones, you don't double count that part. Think of it that way. So they're going to go down if everything's positively correlated. It's more complicated if some of them are negative and some of them are positive. But if all three are positively correlated, so this is when the multiple regression will be they'll be smaller, the coefficients for the homework and the exam slope. Okay, and uncorrelated, so this would be correlated x's. Correlated x's. And here, uncorrelated x's would look like what? They'd be separate. There'd be no overlap. So you'd have homework and exams, both predicting final. And there's no overlap, so you can combine them, and they're not going to change size. Does that make sense? Not if it makes sense. Does it? All right. Now, this will make a lot more sense. A much prettier picture in your notebook. Let's skip this interactions for now. We'll go back to it later. But let's just look at this. This is the, okay, so this is from doing a 3D plot in R. So those of you who are doing R, or in the, and maybe we'll even do it for a bonus, this is making these 3D plots in R of the same, the statistic, you know, we should do this in our bonus. I don't think we've done this yet. But you'll do this in the independent study. Okay, so multiple regression scatter plots. So each of the 107 students has 3 scores, so each student represents a point in 3D space. So here is your homework, here's your exams, and here's the final. So given their homework and exams, given this plane, we're estimating how high up they are here. So the scatter plot shows their final exam scores as a vertical distance from their point in the homework exam plane down there. So for example, this person did terrible on the homework, very bad on the exams too, and then he got a 70 on the final. So the multiple regression equation is that, and it's the best fitting what? You should all know this. What is it going to be? Not the best fitting line, plane. It's the best fitting plane. Okay, that should have been an eye clicker, but all right. Now, what do? Here is the plane, and I drew it here. I hope you can see it in your notebooks. You can see the plane. And here's a picture of this regression plane. And it's the scatter in the scatter plane. Scatter space. Okay, so it's the plane that minimizes the sum of the squared errors. What are these errors? Do you see these errors? This person had a huge error. Look at this person. They scored very high on the final. They were predicted to be in that plane because their homework was under 50. Look at that. And their exams were what? 80. Yeah, that's why. They did pretty well in the exam, but still they did very well in the final. All right, how can we read this? So do you see how the slope of the homework is the tilt of the plane as you go from 30 to 100 on the homework axis? And the slope of the exams is much steeper. So here's this, think of this as the exams here. Let's draw those. So these are people at 100 on the exams. These are people at 90, 80, 70. And those are those parallel lines that we got, that we calculated for people who had 90, 80, and 70. Maybe I can draw them in so you can see what we're doing here. Okay, so for everybody who got a 90 on the exam, this is what the regression line predicts. It's a line through this scatter plane, through the regression plane. and this is for 80, and see how they're parallel. These are the three parallel lines on page 68 that we just did. Those are the equations for them. So those are the lines. Can you see that? Those are those three parallel lines. These, right here. So now you can see where they are in the plane. And the other lines we didn't, these on page, so these are on page 89, excuse me. So that's the three parallel lines on page 89. And how about the ones for the, let's do the other ones too. Well, the ones for the homeworks of 70, 80, and 90. Let's look at that. So can we look at those? Where would that be? This is, the homework's going to be along here. That's 100, so that must be 90 here, 80 and 70. So it's those lines. So, isn't that right? 100, one, can barely see these. Okay, so this is the one for 70. These have a much, and they're parallel too. This is the one for 80, and this is the one for 90. All right, so these are the three parallel lines. Three parallel lines from page 90. And those three are from page 89. Does that make sense? See, these have, this is like for everybody has, this has a very gradual slope of that, 0.1641, and that has a steep slope. So that's pretty much it. And I think we should just leave. I think I'm done. Okay.